A very good morning. Today, we will see a few interesting things. We will see about a term called paradox. Now, a paradox is a logically self-contradictory statement. Like, from one angle, when you look into the statement, you feel that it is true. And then from another angle, when you look at it, you will find it to be false. So that is why I've written over here. It is a statement which you will feel is both true and untrue at the same point of time. Both true and untrue at the same time. It is also called as antinomy. Paradoxes are also called as antinomies. Now look into the diagram over here. You have a small figure over here, and then I've put something over here. No keyboard detected. Press F1. This is an error message which you normally get, like, when you have a problem detecting your keyboard. But, it is actually something foolish. You don't have a keyboard. Your keyboard is not able to be detected, but still they tell you to press F1, which actually is a key on your keyboard. Okay, so it is actually a paradox, something which is true and false at the same time. You don't have a keyboard, which means you have no keys, but they tell you to press an F1. So these are examples of paradox. Another thing which we normally say is like, this is the beginning of the end. Okay, end means, yeah, that's it. You're finished. Nothing more after that. But at times you do hear this particular thing. This is the beginning of the end. So actually end is something which has no beginning. It is the end. But again, this also, it comes under the category of a paradox. It is true, but it is also false. Now, I will see about a few very interesting paradoxes. There is a paradox called the card paradox. Now, the card paradox, you can think of it as a normal playing card. A normal playing card. Now, on one side of the card, you will have a writing like this. The sentence on the other side of this card is true, which means you have two sides of the card. On one side, it is written. The sentence on the other side is true, which means whatever is written on the other side, it holds. It is true. Okay. Now, but on the other side of the card, you have something else written. On the other side of the card, you have written the sentence on the other side. The sentence on the first side is false. Okay, so again, it is a paradox. If you go according to this is true. This is true. Okay, and then if you go according to this is false. Okay, if this is false, it again goes the reverse, reverse, reverse. So actually it is a paradox. When you look from one angle, it is true. When you look from the other angle, it is false. So you can't say which side of the card is false and which side of the card is true. Okay, now first, if you look at the second part, the sentence on the other side of the card is false means whatever is written here, it is false. Whatever is written here, it is false, which means, this whole thing is false. Now let's see another interesting paradox. Okay, now look here, you call it the liar's paradox. There is a person coming up and then he's telling, everything I say is a lie. This man is telling, whatever I say is a lie, which means, he's simply telling, I am a liar. Which means whatever this particular person tells, it is not the truth. It is the lie. Now, if the statement or that liar person is an actual liar, okay, and what he says is true, then, everything is a lie. Whatever he tells is a lie. But, because he tells that everything I say is a lie, this statement, that is also false. So, at the same time, the statement, you can't think it to be either true or false. Or you can say, in other words, it is true. And when you look from it at another angle, it seems to be false. So this is what you mean by a paradox. we'll see a very interesting thing called the barber's paradox. Now, this barber's paradox is actually a small story. There was a small town, and in the village, the town, there lived a barber. In the small town, I went wrong over here when writing. There was a small town, and in the town, there lived a barber. Now, you know that a barber does shaving. But this barber, he does not do shaving for everybody. He only shaves the barbers, shaves the villagers who do not shave themselves. Okay, so in that village, there are people who do shaving by themselves, and then there are even people who do not do shaving by themselves. So this barber, he shaves only the villagers who do not shave themselves, and he does not shave the villagers who shave themselves. So this is the condition in that small town. He shaves only the people who do not shave themselves. Now, the question in barber's paradox is this. The barber is a man in town who shaves all those and only those men in town who do not shave themselves. Okay? The question is very clear. Sorry, the condition is very clear. He shaves only the people who do not shave themselves. Now, the question in barber's paradox is, does the barber shave himself? Does the barber shave himself? Okay. Now, we try getting an answer for our question. Now, let's think about it with the help of set theory. Does the barber shave himself? Now, I have a village. Let's say I think of this village as the universe. And then I have two sets of people in the village. I've only got two sets of people. One is the people who shave themselves, and one is the people who do not shave themselves. These are the two categories of people I have. And of course, they are disjoint sets. I cannot do a union, I cannot intersect them in any way because, it is individual sets. One is people who shave themselves, and the other is people who do not shave themselves. And now I have a barber. Now the question is, where does the barber belong to? Does the barber belong to set A, or does the barber belong to set B? If the barber, he belongs to set A, means he shaves himself. Okay. If the barber belongs to set B, means he does not shave himself, somebody else shaves for him. Let's find out who shaves the barber. Now we need to find out only two possibilities. Does the barber shave himself, which means, does he belong to set A, or does he belong to set B? So these are the only two possibilities which can happen. One is the barber shaves himself, and the other is the barber doesn't shave himself. Now look here, we look into the first case. We look into this case where the barber shaves himself. Now, barber shaves himself means the barber, he belongs to set A. You are assuming, let him belong to set number A. Okay, now set A is what? People who shave themselves. Now, when we think about people who shave themselves, they are the people. When we think about people who shave themselves, they are actually the people who are not shaved by the barber. Okay, when you think about people in set A, they are actually people who shave themselves, which means they are the people who are not shaved by the barber, which means barber is in that set. He is not shaved by the barber, which obviously means barber does not shave himself. Now let us think about the other possibility. Barber doesn't shave himself. Now, barber doesn't shave himself means he belongs to set called B. Okay, he belongs to a set called B. And what is set B? People who do not shave themselves. People who do not shave themselves means they do not know how to shave. The barber shaves them. Okay, so all the people, I went wrong over here. All the people in set B, they are shaved by the barber. They are shaved by a person called barber, which means barber shaves himself. So look here. This first case, we started with thinking the barber shaves himself. And then by the time you came over here, you came into a contradiction and you proved that the barber does not shave himself. Now look here, you started with barber doesn't shave himself, and you came up with a contradictory statement telling that barber shaves himself, which means, whichever case you are taking, you will come into a contradiction. So very simple, the answer is such a barber does not exist. Or what you can think is, the most logical way is you can think that the barber is a woman. If the barber is a woman, it is fine, because the question is about men. You can think about the barber as a woman, or you can even think about barber as not a person, not a man. Like even you can think of it as a mechanized equipment, a robot who does the shaving. Then also it is fine. But still, anyway, such a barber does not exist in such a village. So this is actually a paradox called the barber's paradox. In continuation with the barber's paradox, let's see something called the naive set theory comprehension principle. Now you all know, what do you mean by a universal set? A universal set contains many elements which are components in the set. So you call it like, you say it is a universe. It contains elements of everything. It contains all the elements. You call it a universe. Now, in the naive set theory comprehension principle, it tells that universe is an element of the universe. Okay, you might think it to be weird, but that is how the naive set theory comprehension principle is. Like, the universe, it contains everything. It contains a set of everything, including the universe. So this is what the comprehension principle of the naive set theory tells. You can think it like this. Think of an imaginary bag stuffed with many balls. Now, the comprehension principle of the naive set theory tells that you have a bag filled with many balls, and that bag, inside it, you have that bag itself. Okay, you might sound it to be a bit weird, but anyway, when the naive set theory comprehension principle was framed, this is how the set theory principles were. Like, I just given a small example over here. Imagine you have A is a set of elements 1, 4, 6, 9. Okay, now A is a normal set. You know that 1, it belongs to A, 4 belongs to A, 6 belongs to A, and 9 belongs to A. But when you think about the set 1, 4, 6, 9, it is not an element in A, because you have only 4 elements in A. So normally we say that A is not A is not belonging to A. 1, 4, 6, 9, they individually belong to A. But again, when you take the whole set, 1, 4, 6, 9, it does not belong to A. Okay, so that is one case. That is one case. Okay, now let's think about the other one. 2, 9, and then you have 1, 4, 6, 9. Now A, it belongs to B. Okay, you very well know that A, it belongs to B. 2 belongs to B, 9 belongs to B, 3 belongs to B, 1 belongs to B, and then even this 1, 4, 6, 9 belongs to B. But again, when you look over here, B means it is this whole thing. Again, B is not an element of B. B is not an element of B. So, it need not always be that an element or a set is a member of the set. But when you look into previously what I told you, the naive set theory, it tells that a set, it can be an element of a set. But normally when we see, we find it a bit contradictory, like always sets, they need not be elements of sets. So that is why a mathematician called Russell, he came out with something called Russell's paradox in the year 1901. It is even known as Russell's antinomy. Bertrand Russell, he was a very famous mathematician. He is the author of Principia Mathematica, which is the foundation of mathematics. Now, he came up with a theory. He came up with a theory to prove the looseness of the naive set theory. Okay, so he came up with a proof telling that the naive set theory comprehension principle, it isn't a solid principle. There are some problems in it, and it doesn't hold. Now, how he tried to prove it mathematically is he considered a set called R. Okay, so R is the set of sets which do not contain themselves. So R is a collection of many sets. Okay, R is a collection, or R is a set of many sets, all the sets which do not contain themselves. Okay, so an example is this. A, it doesn't contain itself. When you look over here, B, it doesn't contain itself. So what Russell started off with, I have a set called R, which has many sets. Okay, so if I think of my example, I do have A, I do have the set B, I do have n number of sets, all which they do not contain themselves. Now, the question which he posed is, does R contain itself? Okay, the question he posed is not on S. The question he posed is on R. Will R contain itself? Or if you think mathematically, does R belong to R? Okay, we know that A does not belong to A, B does not belong to B. But in the comprehensive principle of the naive set theory, they told that logically A will belong to A, B will belong to B, and so on. So what Russell tried to bring out is, he tried to bring out an answer for, does R belong to R? So this is how he tried to prove it. Okay, so just like the barber's paradox, he came out with something quite weird, quite confused. Okay, so he started off with this: does R contain itself? So there are two possibilities. R can either contain itself, R belongs to R, or R does not belong to R. So let us think about the first possibility. R is belonging to R. Okay, now we did see in a few examples, or I'll just go back. Okay, now in the definition, you already have this. Okay, R is a set of sets which do not belong to themselves. Okay, I have written over here. Okay, look into the definition over here. The definition itself, it is telling R contains everything which cannot contain itself, or R is a collection of something which cannot be self-contained, which means, R does not belong to R. It comes a perfect contradiction. It comes a perfect contradiction. And now let's see the other part. R does not belong to R. Okay, again, if you look into the definition, all the sets which do not contain themselves, look into the small portion, all the sets which do not contain themselves, they are a member of R. They are a member of R, which means, R belongs to R. I started off with R does not belong to R, and then I came up with the contradiction R belongs to R, which means, does R contain itself? It is indeed a paradox. Okay, you have no answer for that. You have no answer exactly for whether R can contain itself or R cannot contain itself. Very simple. Such a thing doesn't exist. Such a thing does not exist. So this is what is Russell's paradox.